My name is Maureen Haney, and I'm a program manager for the Tutor.com government and federal programs. And it comes as no surprise that math is one of our most tutored subjects here at Tutor.com. And we have gotten a lot of feedback from parents being a little stressed out because they can't help their students with the math homework. So we have done this three-part series on the new math. This is the third one in the series. If you didn't catch the first two, we are going to get those uploaded to YouTube. They should all be uploaded by the end of the day, and we'll make those links available via social media. You will also receive the recording after this. So many of you have access to Tutor.com, which is great, but Tutor.com is not going to be the focus of our presentation today. This is open to anyone and everyone who is looking for some advice with that math. And we have so many experts behind the scenes, including our presenter today, Winona the Math Whiz. She loves math, and her goal is to make you love math too. So on that note, I would like to introduce Winona Young, who is a mentor manager on our Tutor.com instructional team.
Thank you so much, Maureen, and welcome to all of our attendees. I thank you so much for joining today. As Maureen stated, I am one of the mentor managers, I should say, on the instructional team for Tutor.com. And just a little bit about my experience. Like you, I'm also a parent. I have a middle schooler and a high schooler, and I'm the spouse of a disabled Navy veteran. Most of my background is in public education, so I spent about 15 years in the public school system inside of the classroom, about 2 years outside of the classroom. And in that time, I had the opportunity to work with different teachers and students, teaching them about Common Core math and just other math and how to deliver math content to students. I also had the opportunity to write curriculum for the state of Georgia for one of our advanced math courses. For Tutor.com, my role of mentor manager really includes supporting mentors and tutors as they help to create sound educational experiences for students across the country. I also work to create resources for students and for tutors, and to do fun things like this webinar to help educate our students and our parents about the changes in the education space. I am a huge math geek, nerd, call it what you want. I take pride in that. And I'm also a huge proponent of Common Core. So if Common Core isn't your thing and you're kind of groaning and cringing right now, that's okay. But you tuned in, so that gives me some hope that you're at least interested to hear what I have to say about that's not how you multiply. So let's get started. As parents, we may feel like this when it comes to Common Core math. Winter is coming, Common Core is coming, math homework is coming. Even when assisting kids with our homework, our heads may turn a little bit like this as we try to understand what they're doing and why it's so different than the way we learned math. But hopefully today will give you a start to help you feel like this when it comes to helping your kids with homework. I think I just heard music in the background. So how are we going to do that? I'm so glad you asked. Let me tell you a little bit about what we're going to do today. So one thing I hope that we're able to do is to help you understand the conceptual foundations of multiplication. Where did it all start? What does it mean at its core? Secondly, to help you understand the use of the array or the area model when multiplying numbers. And thirdly, to understand the development of the multiplication algorithm that we all know, love, and swear by. So let's start with that very first one. So what is multiplication? This is a question that we don't really think about as adults. We just kind of do it. We say, oh, you just multiply and this is what you do. So we can look at this in three different ways. One, we can look at multiplication as repeated addition. It's a shortcut to adding the same thing over and over again. We can look at it as skip counting. If you ask your elementary school child what skip counting is, they'll be able to tell you right away. Or we can think of it as grouping items into sets of equal sizes. So let's dig just a little bit deeper into each one of these. At its core, multiplication is a shortcut to repeated addition. Let's say we wanted to add 2 plus 2. That's simple enough. We just know that that's 4. But what if we wanted to add it 2 plus 2 plus 2 plus 2 all the way up like 10 times? We could do that easily enough, but there's definitely a more efficient way of doing so. So the idea of multiplication is actually introduced as early as kindergarten and first grade with this idea of skip counting. So just as its name suggests, we count, but we skip numbers along the way. So basically we're counting by some number other than 1. In this example that I just discussed, we could skip count by 2s. So we can do 2, 4, 6, 8, 10, etc., all the way up until we reach 20. And that's great, but if I had, say, 300 sets of 2s, then skip counting would tire me out a little bit. So there's still a more efficient way, which we know and love. We could just multiply 2 by 10, which translates to 10 groups of 2. Now, wait a minute. You just said 2 by 10, Winona. Why is that written as 10 by 2? So it's an English language math translation kind of thing, but this is how students develop the idea of arrays and the idea of the commutative property for multiplication. Again, Winona, what are you talking about? Okay, let's take a look. So 10 by 2 translates for our students into 10 groups of 2. And so with a simple table here, you can see that I have 10 rows and 2 columns. Each row serves as a group of 2, and there are 10 of those. So 10 times 2 means 10 groups of 2. 2 times 10, however, is a little bit different. That means I have 2 groups of 10. So notice that each row has 10 different cells and that there are 2 rows. So, sorry about that, 2 groups of 10 is the same as 10 groups of 2. So let's talk about these arrays a little bit. I didn't hear about arrays until my sophomore year in college. And when I heard about it, it was very complex because I was sitting in a computer programming class talking about housing variables. But our darlings have heard about arrays, again, as early as kindergarten or first grade. So at its very simplistic form, an array can just be thought of as a rectangular arrangement of items. Students use arrays to sort, organize, and represent different mathematical ideas. So as an example, let's say I have 8 teddy bear counters, which is one of the manipulatives that can be used in lower elementary grades. If I have 8 of those, I can arrange them in a few different arrays or arrangements. I can do an 8 by 1, so that's 8 rows, 1 column. Or I can do a 1 by 8, 1 column, 8 rows. Or maybe I want to do a 4 by 2 or a 2 by 4. No matter which arrangement I use of these teddy bears, in each arrangement, they are all equivalent representations of the number 8. So this is how students get introduced to this idea of not just multiplying, but that there are different ways to multiply because of the different types of arrangements that we can make to create representations for a specific number. So let's pause right here just for a minute and give you a chance to interact with me. Let's say I have 12 of these teddy bears. How can I arrange these into an array? And there are several different options. So use the chat or question box to tell me your responses. And you're going to tell me something like this number by this number. So the last example I had 2 by 4, 4 by 2. So the question is, how can I arrange these 12 bears into an array? Feel free to start entering your responses. Excellent. I see Jennifer has responded with 3 by 4. That is definitely one option. What are some others? Okay, we can definitely turn the 3 by 4 around into a 4 by 3. We can use any numbers that multiply to make 12, and we know that as adults, but our kids would play around with these bears and play around with these counters until they get this rectangular array. So they might do all of them in 12 by 1, which 12 columns, 1 row. They put them in a vertical line. Another student might organize them so that they're all in a horizontal line. So we have 1 by 12. Or we could do 6 by 2, 2 by 6, 3 by 4, or 4 by 3. All of these would represent the number 12. Good job there. So after that introduction to arrays, let's talk about how students use these arrays to help visualize or model a multiplication problem. As an example, let's say we want to multiply 2 by 3. Remember that this translates into 2 groups of 3. And our students get a little bit more definition in that they may be able to think of it as 2 groups with 3 objects in each group. So we can arrange these into an array where the first number tells us how many rows we need, and the second number tells us how many columns we need. So in this case, we would need 2 rows and 3 columns. Those bears were really cute to me, so let's use those again. This time we're going to do a nice kind of hot pink color. Students will understand that they need 2 groups of 3. So here's one group of 3, and we'll place another group of 3 just below the first group. Now we have 2 groups or 2 rows of 3 objects or 3 columns. Students would then be able to count up the number of bears to show that 2 times 3 is 6. So again, this is an early introduction. Students are being introduced to the idea of multiplication, but they're just sorting and counting. That's really where it all begins. So then there's the progression from arrays to this idea of area. Remember that arrays are rectangular in shape, and students begin to connect the abstract idea of multiplication to something more concrete, and the area of the rectangle is one way to help them do this. So let's go back to our bears. We had 2 groups of 3, and we know that this is the same as having 2 rows and 3 columns, or a 2 by 3 array. Over time, students can model the bear without the counters, progressing to drawings such as this one. Then each section of the larger rectangle has kind of been broken down. It represents one of the bears. So instead of lining up bears physically with their hands, they can make a drawing and separate their rectangles so that they understand they have 6 bears represented by each, let's just call them cells of that rectangle. Then they can count these smaller sections, which help the students understand that the area of the rectangle is 6. And they understand this because they've been working with this idea that area is how much space is inside of a rectangle. So they would be able to look at this and say, oh, I can count. There are 1, 2, 3, 4, 5, 6 different sections, so the area must be 6. Now, this is not really any different about what we understand about area. We just don't count. So if I remove those bars from in the middle, we just are used to seeing a rectangle. We are told its dimensions, the length is 2, the width is 3. We understand to multiply length by width, and so we multiply 2 times 3, and again, we find that the area is 6. So a concept that we develop or have developed starts again really early in elementary school with this idea of the area model. So here's another question for you, and this one is kind of open-ended. What are your thoughts about using area to help younger children understand multiplication? And you can tell me whatever you think, seriously, whatever you feel, it's okay. So I'd just love to hear from you. What do you think about this area model and how it's used to help our children understand multiplication? I see some responses coming in here. Geometry was my weakest subject. Yes, mine too, until I had to teach it. Shows the units. My child would just count the units contained in the shape. Yes, and that's exactly how they start, which is really good. Good. So just kind of get your brains kind of thinking about what your children are actually learning and how they're progressing through kindergarten, first grade, second grade, all the way up to developing the algorithm for multiplication. So when we see the homework, we say, wait a minute, that's not how you multiply. But it is. At the phase where they are in their learning, it is how they're multiplying. Now, we begin to extend this idea of the area model to help students expand their understanding beyond multiplying single digits. So now we can use the area model to multiply, honestly, with digits of any place value, but we're going to start kind of simple. So let's just take 21 times 3. It's not as efficient to create 21 groups of 3 objects. That means we need 21 rows, 3 columns. We would be arranging bears all over the place. So instead, what we do is use the rectangles as representations of place value. So I'll use a 2x1 rectangle here, since there are 2 place values in the number 21, the tens place and the ones place, and 1 place value in the number 3, just the ones place. So then what we do is we just line up the numbers for the first number down the left side, and that represents, again, the tens and the ones. And then we'll place the 3 at the top. And so this might remind you a little bit of the multiplication chart that we probably got in school. We had to use when we wanted to solve problems, a very manual process. Our teachers wouldn't let us use calculators. I didn't even think we thought to ask back then. But what we do is we take each digit in the first number and multiply it by each digit in the second number. So we'll start with the 2 times 3. 2 times 3 gives us 6, so we place the 6 in the box. Then we move on to 1 times 3. We place the 3 in the bottom box. Then this is, again, at the level of place value. So students would look inside the box and see, oh, I have 6 tens and I have 3 ones. So when they are understanding what this means in terms of place value, they understand that 6 tens and 3 ones equates to 63. So 21 times 3 is 63. Here's another way we can look at this. We can decompose, which just means to kind of break down 21 into its separate place values. 2 tens, or 20 plus 1. 2 tens and 1 1, or 20 plus 1. Then we place the actual values of the digits themselves, so 20 and 1 as opposed to 2 and 1. And then we'll place the 3 across the top just as we have before. There's going to be one difference now because we're using the actual place value and not just the digits. So we're using 20 instead of 2. But the process is the same. We take 20, we multiply it by 3 for 60. We take 1 and we multiply it by 3 for 3. And now we don't have to translate this idea of 6 tens and 3 ones because we just have 60 plus 3, which gives us 63. Students can easily add those together once they're using the actual value as opposed to the digit. Now, how does this compare to the algorithm that we're used to? So let's take a look. We want to multiply 21 times 3. The way we learned it, then we would start with the ones place, 3 times 1, which is 3. Then we come back to the tens place, 3 times 2 would give us 6, 63. Now, is that faster? Absolutely. Is that more efficient? Absolutely. Do our first and second graders understand what that means? No. They would just be following an algorithm that was given to them without having a conceptual understanding of why that works. Now, notice in the algorithm, we start with the ones place. That's the convention, which is just the accepted way to do things. We can actually start multiplying with the tens place if we wanted to. It might cause a little confusion because we'd have to keep up with place value. Beginning in the ones place and having that as a convention really just helps that keep consistency with the algorithm across all of the users who are learning how to multiply in this way. Here's another example, 2 by 2. This area model would have 2 rows and 2 columns. We have 2 digits in 15 and 2 digits in 13. So we do the same as we did before. We separate the first number into its place values. So 15 is composed of 10 and 5, and 13 is composed of 10 and 3. And then we begin the process again of just multiplying. So I'll start with 10 times 10, the upper left box, which would give me 100. And then I'd multiply the 10 on the left times the 3 on the top, which would give me 30. And now I'm ready to multiply by 5. So I'm going to drop down to the bottom boxes and multiply 5 times 10 to give me 50. And 5 times 3 to give me 15. Now, what a student is able to do, similar to what we did before, is we're going to pull all of the numbers out of the box because these represent individual areas and add them together. So they take 100 plus 30 plus 50 plus 15 and recognize that this product, 15 times 13, is equal to 195. This is something called multiplying with the box or multiplying inside of the box. And again, this starts really early, second, third grade. I taught high school. Part of what I teach in high school in algebra classes is multiplying polynomials, like x squared plus 3x plus 5, and multiplying those times other polynomials. I used the box when I taught my high school students how to multiply polynomials because just as it helps elementary students keep up with place value with numbers, it helps high school students keep up with place values when it comes to variables. And they thought it was the easiest thing and wondered why no one ever showed them how to do this. Now, that was before Common Core. Our students learn this in elementary school. So now if they roll into high school, this process will be very familiar to them. They'll say, oh yeah, I did this in elementary school. I just make the box and then I multiply and then I add when I bring everything out. There's a progression of this idea through elementary, middle school, and high school. And that's part of what makes the Common Core so fascinating. So what about the algorithm? Okay, I'm gonna give you a little test. I want you to try multiplying 15 times 13 just using the algorithm that we all learned. Just multiply 15 times 13. And then think about what types of comparisons you can make between what you're doing when you multiply and then the methods that I've shown you. And then if you want to share something to put into the box, in the chat box, just tell me what you noticed, some observations that you made. Take a few seconds for you to do that. You might need it more than a few. Let's take maybe a minute for you to do that. As you're going through that algorithm, you're multiplying the 3 times the 5. You might have to carry a 1. And you move to the 1. We have to move over in a place value. Hopefully some of the things that you're noticing is that we're coming up with those same numbers. For example, when you multiply the 3 by the 5, you get 15. When you multiply the 1 times the 1, we say we just get 1, but what we're really getting is 10 times 10, which is 100. So the algorithm affords us the opportunity to no longer have to keep up with place value, because by the time we reach the algorithm, we understand how those place values work together. Okay, last part, and this one is just really cool. This is the lattice method, which is just another way of multiplying. It's another visualization, helps students keep up with place value. It gets its name from this crisscross style that you may have seen in fencing or in artwork, or if you're a baker when you're making a pie and you crisscross the dough to kind of give it that nice lattice look. That's where the idea comes from. This is what the lattice template looks like. It shows that similar crisscross pattern. Using what we know from the area model, we can demonstrate place values using this method. Each smaller rectangle is separated by a diagonal line, and that serves a purpose because this is where we'll place the numbers that we get when we multiply. By convention, we put the tens digit above the diagonal line and the ones digit below the diagonal line. So let's take a look at an example of how the lattice method works. Let's say we want to multiply 73 times 46. Here's our template. We're going to arrange the numbers a little bit differently this time, and this is just because of the method. It's not about place value, at least not in terms of why we're placing the digits where we are. We're going to place the 7 and 3 across the top, and we're going to place the 4 and the 6 down the right side. And then we begin to multiply. We're going to start with the top right. Again, that's just convention. We can start anywhere we want. If we start with the top right, we're multiplying 3 times 4, which gives me 12. So I'll place the 1 for the tens place in the top and the 2 for the ones place in the bottom. And then I'll move to 3 times 6, which will give me 18. 1 will go above the diagonal, 8 will go below the diagonal. And then I'll move to 7 times 4. We're in the top right, which gives me 28. 2 10s and 8 1s, 2 in the top, 8 in the bottom. And then 7 times 6 for 42. 4 in the tens place at the top, 2 in the ones place at the bottom. Now, let's talk a little bit about the separation that's caused by the diagonals. That's very intentional. Notice that there are 4 sections that are created in this particular problem. These correspond to the place values that are going to occur in our final answer. If we start at the bottom right, that will represent the ones place, and then we're going to move clockwise. So to the left, that would be tens, moving on around and up, hundreds, and then the 4th place value will be thousands. Now what we do is we add along each diagonal. So for ones, we're going to have 8 ones. We start at the bottom. For tens, we have 2 plus 1 plus 2, or 5. For hundreds, we have 1 plus 8 plus 4, which is 13. Now this is where that algorithm kind of comes into play, because our students have learned about place value and making trades or carrying, so to speak, the 1. They understand that if I have more than 10 hundreds, that I can separate that out into 10 hundreds and 300s, and that 10 hundreds is the same as 1,000. So they can trade those 10 hundreds in other words, what we think of as carrying the 1, to the next place value, which is the thousands. And then that leaves them with just 3 hundreds in that particular place. So now when we move to the thousands, we have the original 2,000s that was there, plus we have the 1 that we carried. So we have 3,000s. I know that's a lot. That looks really crazy. And you might be wondering, okay, so what's the answer? Because there's 5 million numbers on the page. So the way we read the results for Lattice is we stay outside of the box and we go to the left side. We read down the left and then across the bottom. So if we pull out what we have after adding, we have 3,000s, 300s, 5 tens, and 8 ones. And again, our students understand place value. So they know they can write that value as 3,358. Nice work. I won't have you practice the lattice method with me, but I just wanted to show you another way that your kids may present multiplying to you and have you going a little nuts because you may not have seen it before. So as we wrap up, what do I want you to walk away understanding or knowing from this webinar? The first thing is that our students are visualizing multiplication before they even get to an algorithm, meaning they are using area models, arrays, lattice methods. There are a variety of ways for young children to visualize multiplication. The second thing is that grouping objects and using arrays or the box or the lattice method are really some of the most common strategies, although there may be others out there. Third, use of each strategy progressively leads to a better understanding of why the traditional algorithm works. And that's the important distinction between the way we learn math and what Common Core is implementing in our schools. That students not only understand how, but now they're also learning why. And then lastly, this is really important. As a parent, you can absolutely support your child's learning of mathematics just by understanding a little bit about the methods that they're using. You can even ask your student to teach it to you now that you've seen a little bit of what we have to offer. And so with that, I want to thank you again for attending. And at this time, I will ask if you have any questions that you want to bring to the floor.
Thank you so much, Winona. That was great. So we have a couple of questions and we have some comments too. One person said that using the area method is easier. This is so great because now I have an understanding of Common Core math. Yay.
Awesome, thank you.
And then another one commented that I've seen YouTube videos on the lattice method, but you just explained it really clearly. Thank you.
Thank you.
So that's good. And we all need a Winona in our lives every day, I think, for this math stuff. So then I have another question. My fourth grader is struggling with her multiplication math facts. How many minutes per day do you suggest she practice for practice and drill type of thing?
So this is one of the things that I think is maybe a misnomer or misconception about Common Core, and that students don't need to know their multiplication facts. They absolutely do need to know their multiplication facts. And I would say keep it really simple and take it back to flashcards. I know we're kind of under quarantine right now, but if you have some laying around, that's fine. If you want to, venture out, I would say like a Dollar Tree or, your local dollar store. But you can even make flashcards at home. Just take some index cards or some paper you have laying around. And I would say no more than 15 minutes. We have to pay attention to attention span and watch for cues of student frustration, but you can just make it like a fun time. It's like, hey, it's flashcard time. Today we're going to work on threes and fours. And you only pull out the threes and fours three and four flashcards and just hold them up. 3 times 1, oh, that's 3. 3 times 7, oh, that's 21. And one of the things I did with my kids when they were younger, once they mastered a certain fact, I removed it from the pile. So over time, we were really only working with those multiplication facts that they were having trouble with. So not a long amount of time, keep it really simple and make it fun. I would say 15 minutes top.
Okay, great, thank you. And then we had another person ask, how long has the lattice method been around? Because they had never heard of this method before.
So this is really interesting. It dates, I can't give you an exact date, but it is an ancient technique that has been traced back to Chinese mathematicians. So we're talking thousands of years. And I think that it's coming to the forefront because a lot of the methods that are used for math in countries other than the US do really focus on this conceptual understanding. And while it looks complicated, the students really do understand how to use it because of the place value. So we're talking about something that's really old back there with like calculus and Pythagorean theorem.